In this chapter, you're going to learn about some fundamental language constructs of GraphQL, such as the GraphQL schema, queries, mutations, and subscriptions. In the second part of this video, I will demonstrate how you can experiment with your own GraphQL sandbox environment to apply what you learned in practice. GraphQL has its own type system that's used to define the schema of an API. The syntax for writing schemas is called the Schema Definition Language, or short, SDL. Here is an example how we can use the SDL to define two simple types. One is called person, and the other type is called post. The person type has two fields. They are called name and age, and are of the types string and int. The exclamation point following the type means that this field is required. Post only has one field that's called title and is of type string. It's also possible to express relationships between types. In GraphQL, that's simply called a relation. Let's add a relation between the person and the post types to express that one person can be the author of many posts. We first add the author field to the post type. Now, every post that is created needs to be associated with a person who is the author of it. Next, we add the posts field to the person type to express that a person can write multiple posts. The syntax to specify that something is a list in the SDL is similar to many programming languages. It uses square brackets. Notice that we just defined a one-to-many relationship between the person and the post types. Let's now discuss how you can fetch data from an API by writing GraphQL queries. When working with REST APIs, data is loaded from specific endpoints. Each endpoint has a clearly defined structure of the information that it returns. This means that with REST, the data requirements of a client are effectively encoded in the URL that it connects to. The approach that's taken in GraphQL is radically different. Instead of having multiple endpoints that return fixed data structures, GraphQL APIs typically only expose a single endpoint. This works because the structure of the data that's returned is not fixed. Instead, it's completely flexible and lets the client decide what data is actually needed. That also means that the client needs to send more information to the server to express its data needs. This information is called a query. Let's now take a look at an example query that a client could send over to a server. The all persons field that you can see in this query is called the root field of the query. Everything that follows the root field is called the payload of the query. This particular query would return a list of all the persons that are currently stored in the database. Here is an example response. Notice that each person only has the name in the response, but the age is not returned by the server. That's because the name was the only field that was specified in the query's payload. If the client also needed the person's age, all it has to do is slightly adjust the query and include the new field in the query's payload. Now, the server will also include the age of each person in its response. In a GraphQL query, each field can have 0 or more arguments if that is specified in the GraphQL schema. For example, the all persons field could have a last parameter to only return up to a specific number of persons. Here's what a corresponding query would look like. Now the server only returns the last two persons that have been stored in the database. One of the major strengths of GraphQL is that it allows for naturally querying nested information. For example, if you wanted to load all the posts that each person has written as additional information, you could simply follow the structure of your types to request this information. So this is what the corresponding query would look like. The server will now resolve this query and include the list of posts that are associated with each person that is being returned. So now we also see that each person has a list of posts in the server response. Next to requesting information from a server, the majority of applications also need some way of making changes to the data that's currently stored in the backend. With GraphQL, these changes are made using so-called mutations. There generally are three kinds of mutations. Mutations for creating new data, updating existing data, and deleting existing data. Mutations generally follow the same syntactical structure as queries, but they always need to start with the mutation keyword. Now let's take a look at an example mutation. Notice that similar to the query that we wrote before, the mutation also has a root field. In this case, the root field is called createPerson. We also already learned about the concept of arguments for fields. In this case, the createPerson field takes two arguments that specify the new person's name and age. Like with a query, we're also able to specify a payload for a mutation in which we can ask for different properties of the new person object. In our case, we're asking for the name and the age, though that admittedly is not super helpful in our example, since we obviously already know these as we pass them into the mutation. However, being able to also query information when sending mutations can be a very powerful tool that allows to retrieve new information from the server in just a single round trip. The server response for the above mutation will look as follows. Notice that exactly as with queries, the server response is shaped according to the mutation that is sent. One pattern that you'll often find is that GraphQL types have unique IDs that are generated by the server. Extending our person type from before, we could add an ID like this. Now, when a person is created, you could directly ask for the ID in the payload of the mutation, since that is information that wasn't available on the client beforehand. Another important requirement for many applications today is to have a real-time connection to the server in order to get immediately informed about important events. For this use case, GraphQL offers the concept of subscriptions. When a client subscribes to an event, it will initiate and hold a steady connection to the server. In this example, the client subscribes on the server to get informed about new users being created. Whenever that particular event then actually happens, the server pushes the corresponding data to the client. In this example, this is the name and the age of the new user, since that's the information that's specified in the subscription payload. Unlike queries and mutations that follow a typical request-response cycle, subscriptions represent a stream of data sent over to the client. Let's assume there are 3 persons that are created by other clients while the subscription is active. The server would then, for each of these persons, push the corresponding data to the subscribed client. Now that you have a basic understanding of what queries, mutations, and subscriptions look like, let's put it all together and learn how you can write a schema that would allow to execute the examples you've seen so far. The schema is one of the most important concepts when working with a GraphQL API. It specifies the capabilities of the API and defines how clients can fetch and update data. It is often seen as a contract between the server and the client, and in general, a schema is simply a collection of GraphQL types. However, each schema will have some root types that define the entry points for the API. These root types are the query, the mutation, and the subscription types. Let's now see how we would have to define these types in the schema to enable all the examples that we saw before. First, to enable the all-persons query that we used in the beginning, we need to add a corresponding field to the query type. Notice that we are also adding the last parameter that we were using at some point to limit the number of users that we wanted to retrieve. The type of the all-persons field is a list of persons, since this is what the query will return. Similarly, for the mutation to create a new person, we have to add the createPerson field to the mutation type, since that was the root field that we used when we were sending the mutation. It takes the name and age arguments that we already used before. Notice that the return type of the createPerson mutation, the createPerson field, is a single person object. Logically, this is the one that was created by the mutation. Finally, the subscription type is pretty straightforward. The root field that we used to subscribe to the event of new persons being created was called newPerson. Consequently, this field needs to be added to the subscription type in our schema. The type of the newPerson field is person. Let's put it all together. Here we see the full schema that defines all the capabilities of our API. It's based on the model of the person and the post types, and then we also define the 3 root types that we just discussed. It is important to realize that despite having defined the post type in the schema, the API actually does not allow any operations on it at the moment. All we can do with the API right now is to read the list of all persons, create new persons, and subscribe to the event of new persons being created. So the post type at the moment is kind of useless. A more realistic and complete version of the schema would define additional operations for both model types. We could, for example, define a CRUD style API by adding a couple of new fields to the schema's root types. CRUD is short for create, read, update, delete, and refers to the 4 kinds of operations we want to be able to perform on a type. The first thing we would have to do is add another field to the query type to retrieve all the stored posts from the server. This field is called allPosts and looks very similar to the allPersons field that we already have in the schema. Notice that with this setup, all we can do is ask for all the posts and all the persons that are currently stored in the backend, but it's not possible to query individual posts or person objects. Next, we can go and complete the CRUD API for the person type. We can do so by adding 2 more mutations, one for updating and one for deleting person objects. The updatePerson mutation takes an ID that allows to specify which person should be updated, as well as the person's properties as arguments. The deletePerson mutation, on the other hand, only takes an ID to tell the server which person it should delete. This completes the CRUD operations for the person type. Let's do the same for the post type. All we do is adding the create, update, and delete mutations for the post type, analogous to how we specified them for the person type. Notice that we also need to add an ID to the post type for the create and delete mutations to work. Finally, to complete the setup, we're also adding the ability for clients to subscribe to all these events on the person and on the post types that we just created. This is a more realistic setup of an API that defines useful capabilities. Notice, however, that the way how we defined the schema still has a couple of flaws. For example, at the moment, it's not really possible to set and modify the relation between person and post. We will leave this as an exercise to you to think about what the corresponding mutations would look like. In general, however, this whole schema already does illustrate the general ideas you need to follow when writing a GraphQL schema. In the next chapter, we'll discuss the big picture and highlight some major architectural components that you'll find in all GraphQL infrastructures.